Thank you very much for inviting me. I would like to introduce the tau performance system here in the context of OpenPOWER. And the tau performance system has a long history. I've been working on this project for about 24 years now. And it is a mature profiling tracing toolkit. It provides support for instrumentation or adding hooks to your program, performing measurements with profiling, tracing, hardware performance counters, and it provides support for visualization. It's widely ported. It supports, our goal is to support all the HPC platforms, and most importantly, it's open source. It's provided in a BSD style license. You can download it with no restrictions on core counts. It integrates very easily with application build environments, and so many HPC tools, many HPC applications use it. This is the architecture. There is the instrumentation phase where we can add hooks to your code, and you can do this at the source level. We support C, C++, Fortran, Python, Java. We have support for MPI wrapper interposition libraries. We can generate wrappers. We can do instrumentation at linking time. We can even rewrite binaries or instrument the code while it's running. We have support for measurements with profiling and tracing, and then finally we generate data that's analyzed using our tools, Ampere, Paraprof, and Perf Explorer, and it also exports to other third-party tools such as Ampere using OTF2. So some of the questions you can answer with tau are, how much time is being spent in key code regions in my code? At the file level, at the loop level, at the function level, and even down to the statements. So you can see exactly how much time was spent in different code regions. We can also see the time spent in OpenMP loops, kernels on the GPUs. We can see how many instructions are executed in these code regions or any of the PAPI metrics. We can look at metrics from KUPTI, higher level metrics like occupancy on a GPU, and correlate that back to the source level. We can see the memory usage of the code, how much memory was allocated, deallocated, what was the memory footprint of your code, add up the stack, heap, data, BSS, all of that, and what is the max memory usage for each process. Is there a memory leak? What is the memory high water mark? You can look at energy usage, you can look at the I/O, you can even see how the application scales. So you can do a lot of analysis on your application using tau. The instrumentation phase or adding hooks to your code can be done either using source instrumentation, using a preprocessor where we can add the start-stop calls in a copy of your code and compile it. We use a toolkit called Program Database Toolkit, PDT, for doing that. And we can also have a selective instrumentation file where you can say, I'm only interested in this region, or instrument at the level of loops in that function, and so on. We also have support for compiler-based instrumentation where the compiler can add a special flag and then generate instrumentation at the routine boundaries. But what is very interesting is that we support runtime preloading of tau's DSO. So you can take a binary with no changes, and just run it with tau, such as tau exec and the application name. And that's a very interesting mode of instrumenting your code. It can generate profiling data as well as trace data. Now, just as to recap, profiling shows you how much time was spent in key code regions. The total time spent cumulative over all the invocations. Tracing, on the other hand, shows you for every entry and exit where the program was spending its time along a timeline. So there is a timeline display. This is the jump shot tool that ships with tau, but we can also generate data for Ampere, and it shows you what each process was doing and where messages were sent and what data transfers took place. With profiling, you can create a profile which has inclusive as well as exclusive metrics. In this case, if there's a function foo that calls an instrumented function called bar, then you see the green region is the inclusive time, and the yellow region there is the exclusive time spent only in that function. So when you look at the profile, you can see exactly how much exclusive time was spent in those functions. With probes, you have start and stop calls, which can precisely measure how much time or data cache misses or counters were spent in that region of code. And we also support sampling. So if you look at performance evaluation tools, there are two classes, profiling cam and tracing cam. In profiling, you have direct measurement or sampling. And Tau supports all of those options where you can generate an interrupt. You don't need to modify the code. But to get the source line information, you must compile it with -G, which we suggest that you do anyway, even if you're using like an O3 option. With sampling, you get a periodic interrupt. It relates it back to the code regions, and then you can see exactly how much time was spent in your code by creating an estimate. With instrumentation, we actually add the start and stop calls to your functions, whether it's done by the compiler or by source instrumentation, and then you can see precisely how much time was spent, and Tau allows you to do both. Yes?
What happens if you have synchronization between start and stop?
So if you have a synchronization call, you can also instrument that and see the precise time spent in the synchronization calls, and it will take care of instrumentation.
Is that automatically or you have to do it?
So it depends on the runtime. So if you have an MPI call, then it's automatic. If you use OpenMP, pthreads, all of that is automatic. And we have wrapper libraries which can intercept those calls and tell you exactly how much time was spent in synchronization and how much time was spent in the exclusive time for that function.
When you use start and stop, are you using actually both time or using CPU time?
It's up to you. You can choose both of them if you would like, or hardware performance counters, or any of those metrics that you like. We can even create a custom clock. Okay, you can create a virtual clock as well. So Tau exec is this interesting tool where you can just intercept calls from the runtime, including MPI, OpenCL, OpenACC, CUDA, pthread, and now even AMD ROCm. And you can select memory instrumentation. You do not need to modify the binary. This is how it works. If your uninstrumented executable is in or out, now you can say Tau exec -kupti for the GPU CUDA profiling tools interface, or kupti-um, or OpenCL, or OpenACC, or ROCm, the AMD ROCm GPUs. In fact, I think Tau is probably the only tool that supports all of those different GPU options. And you can even instrument OpenMP Tools interface using the TR6 level of instrumentation. You can do I/O tracking, you can do event-based sampling. You can even say the resolution of event-based sampling should be coarse, like file, or function, or line. And you can go down to any level that you want. Of course, line will generate a lot more data. You can specify the period for interrupts. You can specify a counter for the interrupts. So you can do quite a bit with just Tau exec. And when you configure Tau with different tags, you can say PAPI with PDT. It creates a stub make file which contains the configuration parameters, where PAPI is located and so on. And then it creates a shared library. So Tau exec preloads that shared library in that directory. And you can then pick which configuration of Tau to use by using a -t tag parameter like this. Once you generate the data, you can launch the paraprof tool to see the performance data. This is the GUI. Here all the colors represent the functions on different MPI ranks. And you can just say don't stack the bars together, so each color has its own separate area. This is the 3D profile browser. This is unique to Tau, that you can see the shape of your application's performance data. It can show you on one axis all the functions and call sites. On the other axis, the MPI ranks, threads, GPUs, and then you can see the height along the third axis, which could be the exclusive time, and the color. So you can measure quite a few things and see what each CPU was doing and what was the shape of the execution. here is an example of using tau with Python, and we are using the Power AI environment with an MNIST example that uses TensorFlow internally. No changes were made to the Power AI environment. Instead of just saying Python mnist.py, you would say tau_Python mnist.py. And then you will see exactly how the GPU's parameters are there. It can show you with exactly how much time was spent in the kernels, and these are, you can see C++ kernels. It can show you the TensorFlow row reduction kernel on the GPU and which thread it executed on and how much time was spent in it. It does demangling. It can show you the details of this operating on specific nodes. You can see the names of the kernels. Sometimes they are long for these C++ frameworks. And you can see the exact kernel parameters on the GPU. You can see the time spent in the thread statistics table, which shows you the time spent in CUDA operations. You can see the time spent in Python operations, and even the C function calls that Python calls internally. So you're taking a slice through the runtime. You're slicing the program and saying, show me all the layers. How much time is spent at the language layer, at the CUDA layer, at the Python layer, and C layer, and see exactly the exclusive as well as inclusive metrics over there. You can see the data transfers as well along a calling path. These are context events. So you can measure the extent of the data transfers, saying there were 3 transfers from so many bytes to so many bytes, and the mean value was so much, and total transfers bytes along this CUDA memcopy operation when this TensorFlow session run wrapper was called by this do run and this figure. So you can unravel the Python call stack as well as the CUDA interactions and see how much data transfer took place. You can see the per thread profiles. This is all done on the IBM Power platform. And you can see the thread statistics window where you can, even if you don't have simple information for libraries that are just stripped, you can still see the names of the libraries. You can see what was the time spent in that. So you could see that CUDA free function called this libglibc, and it called the libcuda.so in this location, or these are the functions, or the time spent in pthread mutex lock in this PowerPC 64 libpthread was so much. So you can understand what's going on even by the names, the descriptive names of the functions and the libraries that they come from. Here is the 3D view for the cafe uninstrumented code run with tau for the GoogleNet example. And we have a paraprof manager window which shows you the characteristics of the GPU, how the application was run, and in this case, this is the cafe GoogleNet benchmark, and you can see the time spent in AlexNet, GoogleNet, the ref RCNN, and then compare them with each other in an example. This is the node view of paraprof that shows you how much time was spent in, say, CUDA event synchronize. Just like you were asking, if there's a synchronization operation, you can see the exact time spent in the CUDA event synchronize code over here. Or in this case, you can see how it was called, and within that synchronize what it did. For example, CUDA event synchronize calls the GIP thread once call on the IBM systems, and you can see how much time was spent exactly in that by taking those samples. So you can get a lot of information within those calls and target this. Because tau is made in a modular way, you can assemble components together. So you could say, I have a P thread with CUDA, with Python on the IBM system, and show me performance data from all of those different layers. We have also done quite a bit of work with MPI, and this is joint work with the Ohio State University, where we use the MPI Tools interface and go inside the runtime and change the parameters. You see, MPI is a complex runtime. There are about 400 parameters how do you know that it has been tuned correctly for my system? So tau can exchange information with the runtime with this bridge called MPI Tools interface. And then it can query the performance variables, figure out how much congestion is there at the network interface. It can look at the amount of traffic that's going on by the reduction operations, and then change the thresholds that are not statically set at the beginning of the program, but can be dynamically tuned using a plugin architecture that tau provides. So even if you are developing a new performance tool, I would say please consider using a plugin for tau, so you don't have to redo all the other stages of instrumenting those different libraries. You can just plug right into the measurement layer and say, give me those events, and I will just do this with that. And even store the data in tau format and show it in paraprof. So creating new tools becomes very easy with this plugin architecture of tau, and we have used it for auto-tuning workflows. So for example, this red portion shows the MPI time, and green portion shows the rest of the application time in this Vampire view. Vampire is a trace visualizer that comes from TU Dresden in Germany. It's an excellent trace visualizer. It's the state of the art. And here, I have used the MPI Tools interface to dial down some of those parameters, change the thresholds for eager versus rendezvous protocols based on how much communication is going on in my program. And now you can see that I improved the total runtime, and this MPI red portion gets reduced considerably over there. So the total time spent in MPI operations is changed with no change to the binary. It's like putting on a stethoscope and figuring out how much time was being spent in MPI and dynamically changing the knobs that MPI provides. So this can be done with tau. Yes?
And this tool is working on MPI Tools.
MPI Tools, and it's installed with IBM systems with GPU support.
And when the run to modify the parameter stops,
Yes.
the original parameter are restored, or?
So they are stored in the tau profile, saying this was the original value, this is the new value that we changed to, and then this is the control variable that was modified within MPI.
Yeah, I was saying, when the run stops,
Yes.
the original values are restored, or?
No, this is on a per application basis. It's only with tau. So you say tau exec a dot out, it can dial down the parameters and improve the performance of the MPI runtime. And when it exits, the MPI system defaults are just the same.
Okay.
So this is just an example. We can do source instrumentation using PDT, the Program Database Toolkit, and it can take the source code, parse it, instrument it in a copy of the source code. Here is an example, a classic CFD code called Fun3D from NASA Langley. And here you can see the time spent in a call path profile with source instrumentation of everything. And then you can see how much time was spent in, say, the point solve 5 or 5-point solver on each rank in the MPI. And this is the call path profile that tau can produce. There are many different parameters in tau. You can just set them by changing, say, tau trace, call path, tau sampling, communication matrix, turn on call sites, so you can see exactly how much time was spent at a particular location in the source file, and change metrics. You can do a lot more with event-based sampling. You can even track load on the system, change the filter file and say, I want to instrument this, not that. You can do OpenMP instrumentation, again, without any modifications to the code, and see all the memory instrumentation parameters. You can download tau from tau.uoregon.edu at the Performance Research Lab or from the HPC Linux distribution. This is where the development takes place. We have a very active visitor program in Eugene, where we are located in Oregon. Please consider, if you have a big code, coming to Eugene, spending a day or two with us, and we can work with you on your applications. If you would like to try it on our machines, we can enable access to our power systems. We have Power 8 right now. We are getting a Power 9 soon. And so if you would like to get access to our machines or some inferencing hardware that we have, please talk to me offline. we'll be able to support that. I would like to thank the sponsors for this project, in particular the US Department of Energy, the Exascale Computing Program, the Oak Ridge National Labs, Argonne National Labs, the Office of Science Contracts, the SIDAC, Lawrence Berkeley National Labs, the Tri-Labs, Livermore, Los Alamos, Sandia, the ASC NNSA, Battelle PNNL, and Oak Ridge, the Department of Defense, the HPCMP, the National Science Foundation, NASA, the CEA in France, IBM, and our partners at the Ohio State University, the developers of MPI Tools, MPI Tools Inc., the University of Tennessee, Knoxville for PAPI, the TU Dresden, Germany for Ampere, and Jülich Supercomputing Center for the developers of SCORE-P, OPARI, and numerous other collaborative projects. Thank you. Any questions? Yes?
This auto-tuning capability thing, how adaptable it is for the system. I was thinking like another thing like this would be like sharp, and how the hardware collector has hundreds of parameters that you can tune.
In fact, sharp.
Is there any work in our
Yes, there is work. We have published a paper, in fact, got the best paper award at Euro MPI, and we used Sharp's auto-tuning by looking at the collective operations, how much time was being spent, and saying, what if we didn't do these collectives on the host? And if we pushed it to the network interface in Mellanox using the Sharp protocol, and MPI has this knob. It says, please use Sharp. And then we enable that knob based on the performance data that we're collecting at runtime. And of course, you get incredible benefit from using the Sharp protocol in Mellanox. You have to have the drivers all installed on your system to enable Sharp. But once that is done, Tau plugin can do this, and we have demonstrated that. Yes, thank you for.
And then
Is the process for that, you go through the runtime, it actually does the profiling, and
Yes.
then it will recommend, or it will have those parameters, so it's not dynamic, and then you run it again, and it'll
So
implement
there
those?
both modes are available. There is one mode, exactly as you say, where Paraprof shows you the performance and it gives you recommendations in the Paraprof Manager window. And then you can set that recommendation and run it. Or you can use the auto-tuning plugin where it can look at the data at a certain point in your code and then evaluate it and then change the parameters based on what it finds. So both options are there. And you can define your own plugin. Tau can just give you those events.
Yeah.
So just a quick question. So
Yes.
what's the impact of using Tau in terms of performance of application? So,
What is the impact of Tau for the performance? So, if I use any tool, there is going to be some runtime dilation. Okay. Now, with event-based sampling, you have support for periodic interrupts. There is a fixed overhead. With source instrumentation, you instrument a function. We have support in Tau to throttle the execution. So runaway functions like min, max, or swap that gets instrumented, which get called 1 billion times in your code, will only execute for the first 100,000 times, and then they'll get disabled at runtime. So we have support for controlling the instrumentation at runtime, and with event-based sampling, you can just increase the period for samples, and then you can reduce the overhead. So overheads can be anywhere, from 5% to 10%, or even I've seen overheads go down to like 0.3% for a long-running program, where it makes sense to just keep Tau instrumentation on all the time in those cases.
so let's say if you instrument an application with a sampling time of 1 second or 2 seconds, what would be the overhead?
So the overhead, of course, will reduce if you have a very long sampling period. And yes, you can see negligible overheads in that case. We are talking about like 30 milliseconds instrumentation, sampling by default. If you dilate it to 1 second, you'll probably not see any overhead at all in the code. Any other? Well, I'm here all day. Please feel free to stop by and chat with me if you would like to know more about our tools. Thank you.
Thank you.